So today we're going to talk about logarithms, and then we're going to talk about sequences and series a little bit, and that's what your next 2 weeks of work will be about. Remember, we're not going to meet next Monday because it's Memorial Day. They're doing the food program still Monday, Wednesday, and Fridays, but Monday it's not because of the holiday. We would have been closed for school anyway. So no class on Monday. This will be the last time unless you guys have questions. Remember, you can email me even after class is technically over. Feel free to email and ask questions if there's anything that you need to know. So we're going to talk about logarithms and kind of where they came from, why we have them, why they're useful. Basically, they were invented out of necessity because we have really good calculators and computer programs that can calculate these things for us. So today, maybe we wouldn't have come up with logarithms, but a long time ago, when they didn't have really good calculators or really good computer programs, they needed a way to deal with exponents, a different way to deal with exponents. So really, this happened way back in the 1600s, and scientists, especially astronomers, needed to calculate things that had really big numbers. So think about, we use scientific notation. That wasn't really handy for them to use. And they were doing all of this by hand or on paper, and it was taking a lot of time to do all of this computation, so they needed something better to use. And they built slide rules. I don't know if you guys have seen a slide rule or not. I have one, but it's downstairs. But it's a way that we can make computations more quickly. It's not a calculator. It basically looks like a ruler, but the middle piece of it slides side to side, and you match up pieces to do calculations, like a really fancy abacus. But they use these slide rules and they use the logarithms to do these bigger calculations so that they didn't have to do it all on paper by hand. So just because we have really good calculators and better ways to make these computations, we don't have to do it all by hand, doesn't mean that they're not still useful. So we still use them, especially when we're measuring pH or acidity. We use logarithms. The Richter scale, the scale that we use to measure earthquakes, we use it there. Sound intensity, when we measure decibels, we use a logarithmic scale. So it's still there. We still use it. It's just in a different way. It's not to make our calculations easier. It's just a way to make things look nicer. So think about going back. We're going to kind of set this up. You started out when you were in elementary school learning how to add things together. So once you learned how to count and you knew what numbers were, we started with addition. That's the most basic operation that we can learn is addition. So you started adding things together. Well, after that, we got to repeated addition, and we found out that repeated addition could be simplified by using multiplication. So we switched from repeated addition to multiplication. Well, if you do repeated multiplication, we can write that as an exponent. So we kind of have this whole development of what our math classes look like. Addition, 4 plus 4 is 8. 4 plus 4 plus 4 is 12. But instead of just continuing to add those on like that, we could do multiplication instead. So 4 plus 4 plus 4, that's 3 4s. So 3 times 4 is also 12. Or in that next example, we've got 3 times 3 times 3. That's repeated multiplication. We can rewrite that as an exponent. So whenever we write it as an exponential form, that's what that's called, we know what that looks like, but we're going to change the form and write it as a logarithm. So let's look at an example. So there's our exponential form. This is what it looks like. B is the base, the x is our exponent, and our y is the result. So we could do 2 times 2 times 2. our 2 cubed to get 8. Now, if we wanted to change the form and write it as a logarithm, logarithmic form looks like this. Now, we can switch from one to the other. These two, let's see if I can fit all this on the same screen. There we go. So 2 cubed equals 8 is exactly the same thing as log base 2 of 8 is equal to 3. So the only thing that happens, the base is always the base. So the base of the exponent over here is still going to be the base of the logarithm, so the little number at the bottom. Of 8, so that was our answer from this other one. That's going to be the result, or in this case, it's called the argument. And the exponent's actually the answer. So this helps us solve things for our what if I had 2 to the x power equals 8? Well, my exponent becomes the answer, so I could type that in and get the answer is 3. Your calculator will actually do this part for you. Now, speaking of your calculator doing it for you, not all calculators will change the base for you. So your calculator is really handy in that you can type it in just like that. Let me show you. Okay, so to get to the one that we want, if we want to type that log base 2 of 8 in, if you press F4 to go to math, see this log AB choice for F2? That's the one we want to pick. Now it'll let me type it in exactly the way it looks. So I can do log base 2 of 8 and get that the answer is 3. Now there is a log button on your calculator down here next to the variable log. And if you type that in, oops, just once, and did log of 8, you get something different. Now that's because the base matters. And our default is always going to be that we have a base of 10. So if there's nothing there, then there's a 10 there. But for this one, we had a 2, so we had to change it. So log base 2 of 8 equals 3. Now our calculator, like I said, lets us type this in. We just have to go to math and log AB, and it lets me change that out. But some calculators don't have that option, or some programs don't, and they'll only do things that are base 10. So if we do log of the big number divided by log of the little number, it'll give me that same answer. So let's say I didn't know that I could type it in like this. I could do log of the big number. Divided by log of the base or log of the little number, and still get that right answer. So depending on what your calculator will do, we know how we can type it in. So if we have to, we can do log of the argument over log of the base and get that same answer. So kind of like when you have a square root and we don't have the little number, remember we can take cubed roots, fourth roots, fifth roots, and if there's no number there, then we know it's a square root, but if there is a number there, then we know it's a different root. This is the same way, but this time it's 10. If there's nothing there, we know it's a 10. That's the default. That's what it goes to if you don't change it. So if we did log of 100 and just typed that in, we would get 2. Or if we did log base 10 of 100, we would get 2, because the automatic is that we've got that base of 2. So let's look at a couple of examples, and I actually want to write these down. Make sure I don't get my papers switched around. Okay. So what if we want to change we want to write this in exponential form. So if we have log of 1 over 100 is equal to -2, and we want to change that to exponential form. So instead of having a logarithm in it, we want it to be an exponent. Remember, the default here is 10. If there's nothing there, the base is 10. So remember, this is the base, this is the exponent, and this is the answer. So base, exponent, answer. Now we could type both of these in and make sure that they work. If you type in log of 1/100, we get -2. If you type in 10 to the -2 power, then we get 1/100. So we can see that they interchange and that they both mean the same thing. So a big part of this is just knowing how to change from one form to the other form. Let's do one more like that. So if we have one like this, log base 8 of 64 is equal to 2. Remember, the base is still the base. The exponent comes from the answer, and then the argument is the answer. Now I know that 8 squared is 64. 8 times 8 is 64. So that one works out, and I can follow it. Let's switch it around and go the other way. Write in logarithmic form. So what if I want to switch it and I want to go from having an exponent to something that has a logarithm? So like 3 to the 8 is equal to 6,561. So I could type that in my calculator and get the answer, but what I want to do is change it from one form to the other. So remember, this is the base, this is the argument, and this is going to be the answer. So log base 3 of this whole thing, 6,561, is equal to 8. So 3 to the 8th power is equal to that whole big number. Let's look at one more. What if I've got 5 to the 0 is equal to 1? So to change it, log, the base is always the base. So the base of that exponent is 5. The base of my logarithm is 5. And then the 0 and the 1 basically change order. So the 1 comes first, and the 0 is the answer. That exponent's always the answer. So how can we use this? What makes it useful? So let's try solving an equation with this in it. So if I gave you 25 is equal to, let's say 5x. If I gave you that equation and said solve it, how would you get the x by itself? Divide by 5, right? So you've got to do the same thing to both sides. We've got to do the opposite. So the opposite of 5 times x is that we have to divide by x, or divide by what's beside the x. 25 divided by 5 is 5, and we know that 5 is equal to x. So what if we switch it and say 25 is equal to 10 to the x minus 1 power? How do we get the x by itself? We're going to have to change something. I can't undo a base 10. So if we've got a variable in an exponent, then we need to use logarithms. We need to change the way that problem looks so that we can solve it. And we can use our calculators to help us, just like we could do 25 divided by 5 in the calculator, and we could get the help to solve it. We need to rewrite this. Now I'm going to switch it around so that my exponent part comes first. So I'm just going to trade sides and write the 10 to the x minus 1 first and the 25 second, because that's the way we've been writing stuff when we change form up here. So we're just going to keep it the same. All right, so let's change it. Let's write this in logarithmic form. So log base 10. And remember, that's the default base, so we don't technically have to write it, but we can. Of 25 is equal to x minus 1. That whole exponent is what we're going to set it equal to. Now this part, no variables left on this side. I can just type that into my calculator and see what it's equal to. If we do log base 25, or log base 10 of 25, we get this long decimal 1.3979, and it goes on 40009. So if you type it in, you get that long decimal. And then we know exactly how to solve that. We just need to add 1 to both sides to get that x completely by itself. So all I did was type this into my calculator. You can see I typed in log of 25. I could have typed in log base 10 of 25, but it means the same thing. And then if I add 1 to both sides, a lot of times you'll know how many decimal places you want to round to for problems like this. For this one, I'm just going to round to 3 decimal places. That's usually far enough. This is going to be 2.39, and if I use that 9 to round that 7, I'm going to get 2.398 is equal to x. Now remember, if you go back and plug it in and check it, I didn't round it, so it's just going to be really close. It's not an exact answer, it's a rounded answer, so it won't be perfect when you plug it back in. Okay. So logarithms and exponents are inverses of each other, just like we did the opposite of multiplication, which was division, to get the x by itself in that first example. We did the opposite of exponents, which is logarithms, to find the answer for that second example. There's one other special kind of logarithm, and it's called a natural log, and not like natural log like you found it out in the woods, but natural log like it occurs in nature a lot. So what is a natural log? Natural log has a very special base. The base of natural log is e. Now, if you find the e button on your calculator, you'll find that it gives you this long decimal. E is kind of like pi. So pi is 3.14159. It's a decimal that goes on forever and doesn't end. It's irrational. E is similar. So E happens a lot in population. It happens a lot in interest for like checking banking accounts. And so E is a very special base. Now, we could look at where it comes from. It is kind of fun to find out where that limit comes from, 2.1828, that whole decimal, but we won't do that today. That's okay. But anytime you see natural log, it has a base E. So natural log is just ln. That's the button beside regular log on your calculator. So we've got log right here, and then natural log right here. And notice that the secondary command here is an e to the x power. Notice the secondary command here is 10 to the x power. That's because log has a base 10 and natural log has a base e, and it connects that for us. Okay. Okay, so there's 2 different kinds of sequences and series. One is called an arithmetic, and the other one is called geometric. So arithmetic Think A for addition. Every day, a radio station asks a question for a prize of $150. If the fifth caller does not answer correctly, the prize money increases by $150 each day until someone answers their question. So let's say they start the program today, the caller would get $150. They got it wrong. So tomorrow it would be 150 plus 150. The next day, it'd be 150 plus 150 plus 150. So it adds 150 on every day that they get it wrong. So let's say it started today. This would be the prize money. Tomorrow, if somebody didn't get it right today, this would be the prize money. 150 plus 150 is 300. Add another 150. It'd be 450 for Wednesday, another 150, it'd be 600 for Thursday, another 150, it'd be 750 for Friday, and we could go on forever, right? So that is called a sequence. It's a list of numbers in a certain order. Each number in that list is called a term. So this is an arithmetic sequence. We add a number to each term to get the next term. So that's what this says. An arithmetic sequence is a sequence in which each term after the first term is found by adding a constant called the common difference to the previous term. So think about like counting by twos. 2 plus 2 is 4, plus 2 is 6, plus 2 is 8, plus 2 is 10, plus 2 is 12. And we could go on forever counting just like that. We're just looking for the pattern when we want to complete this. So find the next three terms in the sequence. If I had this list of numbers, 2, 5, 8, 11, 14, well, if I look at this, every single time I add 3 more. So 2 plus 3 is 5, plus 3 is 8, plus 3 is 11, plus 3 is 14, plus 3 is 17, and then 20, and then 23, and then 26, and then 30, or then 29, and then 32. So we could go on forever, adding on number, the same thing. So the common difference here is 3. You can take any two terms and subtract the latter one from the former one. So like 11 minus 8 tells you what you had to add to 8 to get 11. 14 minus 11 tells you what you had to add to 11 to get 14. So you're just looking for that pattern to go on forever. So we can look at this lots of different ways. They don't all have to be positive, or they don't all have to be written a certain way. But when we're talking about arithmetic, it's always when we're talking about adding things. Now, when we talk about the sum of all of those numbers, so what if I wanted to add them all up? That's called a series. So a sequence is the list of numbers. The series is the sum of all of those numbers. So like, let's look at this one. The series is the sum of all of the terms in a sequence. This one's really easy. All I'm doing is adding 1 each time. So the sequence here is 1, 2, 3, 4, 5, 6, 7. The series is what happens when I add them all together. So 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 gives us 28. Okay, so that's the difference. Now, this wouldn't be Algebra 2 if we didn't have some sort of a special formula that we could use to find any term in the sequence or the series for any set of numbers. So the sum of a series looks like this. Usually we would use S for sum of however many terms we're looking at. And I'm just rewriting this so it looks like we would usually write it. So N is how many terms we're dealing with. These little numbers at the bottom, this means the first term in our sequence, and this is the last term in our sequence. So if we know the first and last for whatever we want to find the sum of, it looks like this. Find the sum of the first 10 terms of the arithmetic series where the first term So term number 1 is 6. And the 10th term is 51. Now, I don't know all of the numbers. I don't have to know them all to find the sum. All I have to do is know where I'm going to plug this information into my equation. So S10, I'm looking for the sum of the first 10 terms. So 10 over 2, that's how many terms I have divided by 2, times 6 plus 51, that first term and that 10th term added together. So without knowing all 10 of those numbers, I can find out what the sum of them would be. So this is kind of a shortcut so that I don't have to find all of those 10 numbers and then do 6 plus whatever and keep going forever. Or it might seem like forever. Now sometimes I need to find a certain term. So let's say I've got this pattern and I say, here's the first 5 terms in this sequence, find the 50th. Well, even if you're counting by 2, that can be kind of tedious to get to the 50th one. So like 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, that's just the 10th term, and I'm supposed to go to the 50th term. So especially if I'm going to go to the 50th term, the 100th term, surely there's an equation that I can use to figure this out. So let's say I'm supposed to find the sum of the first 50 terms of this sequence. And I know that the first term of the sequence is 28, and the common difference is -4. Well, if I'm going to use this equation up here, I have to know the first term and the 50th term. I know the first term and the common difference. I don't want to do 28 minus 4 minus 4 minus 4 50 times. So we have an equation for that. This is our formula. Now, had we been in class and had we had the SOL and the final and all that stuff, then this would be one of the equations. All of these formulas are ones that you would be given. So you wouldn't have to memorize these. Okay? So these aren't ones that you would have to just know. These are ones that you would have on a formula sheet. So for this one, we can find any term. So AN, I can find any term. If I know the first term, the number of the term that I'm looking for, and the common difference. So if I want to find the 50th term, all I have to do is plug in these pieces. Sorry, guys. So the first term is 28. I'm looking for the 50th term, and the common difference is -4. So if I plug all of this in, I can just type it into my calculator, and that means the 50th term is -168. So now that I know the first term and the 50th term, I can find the sum of all of those together. So the sum of the first 50 terms of that sequence, 50 over 2 times 28 plus a -168. The other notation that we might run into that you might see is called sigma notation. So sigma notation, this is an uppercase Greek letter sigma. And sigma is just a fancy way to say sum. So I'm looking for the sum of all of the terms from 1 to 5. And this is the pattern I'm looking at is n plus 1. So if I plug in everything between 1 and 5, if I plug in 1 here, it's going to be 1 plus 1. If I plug in 2 here, it's going to be 2 plus 1. If I plug in 3 here, it's going to be 3 plus 1. See this pattern? And then the sigma sign means I add all of those outcomes together. So basically, this is just 2 plus 3 plus 4 plus 5 plus 6. So just know if you see that weird looking E, that's a sigma, and it means sum, that we're going to add them all together. Okay, so those are arithmetic sequences and series. A, arithmetic, or add. We're adding together terms to get from one to the next. Let's look at geometric, and then we'll be finished. So if we look at geometric, remember arithmetic was for add, geometric, and there's not really a way to remember this, it's multiplication. So think about, we're going to change from our example of a radio station, we're going to change it and talk about paychecks. What if your paycheck started at $100 a week, this is a pretty good deal, and doubled every week? What would your salary be after 4 weeks of work? So this is what my pattern looks like. Week 1, we make $100. Week 2, we make twice that, so $200. Week 3, we make twice that, which is 4. And then we double it again to get to 8. So after 4 weeks, I'm bringing home $800 for that week. If I went again, twice 800 would be 1,600. So that's what geometric series means. We're multiplying by the same thing each time. So arithmetic, we add the same thing each time. Geometric, we multiply by the same thing each time. That's what this little definition says right here. A sequence in which each term after the first is found by multiplying the previous term by a constant value. Now this time the constant value is called the common ratio. And if we need to find the common ratio, sometimes we can just look at a sequence and figure it out. Okay, so if you can see the pattern, then it's great. And we can just look at it and say, oh, to get from -3 to -15, we multiply by 5. And then we can check it and make sure it works for all the rest of them. But if we don't just look at it and know, if it's hard to figure out, then we can divide. -15 divided by -3 gives us a +5. And if we check all of them, -75 divided by -15, that's a +5. So we know what the pattern looks like. Now, just like for arithmetic, we can find a pattern and we can find our equation. So if we know what our equation looks like, then we can find any value in that list. So A1 still is the first term. R is the common ratio. So whatever I have to multiply each time to get from one term to the next. And N is whatever number value that I'm looking for. So we've got that equation. And again, that's not something you would have to memorize. That's one of those that you would be given each time. So you wouldn't have to memorize that formula. Now, sequence is the list of numbers. Series is the sum of the numbers. So if we're looking for the series, we want to be able to add all of those values together. So for this one, I can see that I'm multiplying by 3 each time. So this is a geometric sequence. 1 times 3 is 3, times 3 is 9, times 3 is 27, times 3 is 81. And the series, that's the sequence, the series is what happens when we add all of those together. So if we did 1 plus 3 plus 9 plus 27 plus 81, we would get a sum of 121. And of course, we have an equation for that too. So remember, the A's tell us what term we're supposed to plug in. Now there's 2 different options for this one. I don't really like that first option because it's a little bit more messy. I like this one better. If we can get it clearer. So this is the first term times 1 minus the common ratio raised up to the n power. So however many we're looking for the sum of. So if we're looking for the sum of the first 5 terms, we would plug in a 5 there, divided by 1 minus that common ratio. So in this case, the first term is 1. So I'm looking for the sum of the first 5 terms. The first term is 1. 1 minus the common ratio is 3. I'm looking for the sum of the first 5. That's what it would look like when you plug it in. And if you type that in, we're going to get 121, just like when we added all of those together.